Again, thank you all for being here. And I just want to preface the beginning of this talk as saying that, unfortunately, astrophysics tends to be one of these sciences that has a lot of jargon. And throughout the talk, where possible, I have done my best to remove jargon from my explanations of various things. But if at any point you have any doubts or questions about what I'm talking about, or some of the words that I'm saying are just absurd and don't make any sense, please just interrupt me and let me know, and I'd be happy to clarify them. And I'm happy to take questions both during and after the seminar. So the work that I'm going to be talking about is work that I did primarily at NYU over the past few years. And in fact, even though I've left academia, it's still ongoing. I have a referee report to deal with after this. So, the fun never stops. But the primary results of the work that I'm talking about are mentioned in these two papers, which we submitted last year but have now been published. And the work that I'm talking about mainly in this is the bottom paper here. But these are both astrophysics papers, so they really do focus on some of the astrophysical aspects of the work that's being done. But one of the very interesting things about this work is that it leads to a very beautiful result, in our opinion, and it uses a technique that is novel to astrophysics, this idea of looking at mutual information. And I'll define that later on in the talk if you're not familiar with it. But certainly when we were reviewing the literature, we noticed that this was not a topic that people had previously used in our field. And so in fact, we had to include an appendix to explain what it was and show examples and things of that nature. But I understand that it's quite commonly used, particularly in the cell biology community and genomics as well. And in fact, a lot of the R packages that I found to do mutual information have been written by biologists. So I'll get started. I just want to provide a brief outline of what I'm going to talk about today. As I said, I'm going to provide a sort of as gentle as an introduction to the astrophysical problem, as jargon-free as possible. In fact, I'm going to show videos to begin with, just to sort of set the stage and give an idea for the scales that we're looking at. And then I'm going to discuss the specific hypothesis that we tackled, or rather the specific problem that we were interested in tackling. And then finally, I will go on to discuss our application of mutual information, giving a definition of what it is, as well as how we used it in the results that we derived from it, and then provide some concluding remarks and show some outlines of the work that these results are enabling now. And so while those future works don't use, techniques like mutual information, they rely on the acceptance that the results that we get from this technique are providing us with some, interesting insight into the processes that are going on inside galaxies. So just to begin with, I'm going to show you this video produced by the American Museum of Natural History called The Known Universe. And you can find this on YouTube, and I won't have time to go through the whole thing, but I'll show you the beginning. And really the purpose of this video is to give you a sense for the scales that we're talking about here. So what this video will show is a zoom out from the Earth out to essentially the very edges of the universe. And will, or it should, okay, it's going. It features real information or real data at every step of the way. Let me mute my video just in case there's any feedback. Yes, so the background images that you see, for example, of the stars, those are all the actual positions of the stars. This is satellite imagery. It's all as it would be in space if you were looking at this data yourself. Oh, sorry. Little technical glitch. Let me skip back to where we were. I hope we can skip back. Oh, gosh. Okay, perfect. Yes, and another thing to look out is as we zoom out, this video will show you the time it takes to travel from the Earth to the various celestial bodies that we're seeing in units of light travel time. So this is how fast you would be able to get there if you traveled at the speed of light. So in the background, you might recognize some familiar constellations like Orion. And now what we're seeing is distributions of artificial satellites around the Earth. And their trails and everything. One thing that I found very striking about this when I first watched this is just how relatively close these are to us compared to our natural satellite, the moon. And you'll see that shortly. These are all, of course, a lot of them are mixtures of geostationary satellites. Others are used for telecommunication and things of that nature. And then as we begin to zoom out a little bit more, you see that there's a wider distribution of scales. And now the video will begin to pick up a little bit and start showing us kind of a better sense of scale. So now we're approaching 1 second of light travel time from the Earth, and we see the orbit of the moon. And now the planets are going to begin to pop up in the background. And again, just to emphasize, everything that you see in the background here, this image of the galaxy, the positions of these stars, this is all based on real data. And we have, using telescopes, we're able to measure these positions very, very accurately. So now, of course, we've hit the edge of the solar system. We're zooming out to see the more distant planets. Now we've reached one light day of travel, and we see the familiar constellations in the background. But of course, one interesting thing here is that as we zoom out further and further out and really lose our ability to the solar system and go out into what we call the interstellar medium, the actual positions of these constellations will be distorted because obviously these stars are moving in three-dimensional space. The 70-year-old bubble or 70 light-year bubble is the extent of humanity's radio signals. And now, of course, we're reaching the edge of the galaxy, where we live in one of the sort of the peripheral spiral arms of the galaxy. And now we're about 100,000 light years. And we're moving now to the phase of the video that really deals with the data that I'm interested in, which are studying these large collections of galaxies. So now each of these points is a galaxy that we've mapped so far. And this goes out to about 100 million light years. And I'm going to pause the video here, just brief. Oh, I thought I was going to pause it. Sorry. I'll see if I can catch that frame again, but if not, that's all really I wanted to show. Here we go. So this frame, I think, gets a good understanding of the large-scale structure of the universe. And this was really a topic of interest for me during my PhD. And what you can see here, and I will show in greater detail later, is this web-like distribution in the galaxies of the universe. So it's not, it's not a random field. It's not like Gaussian noise. In fact, it's not possible to reproduce the two-point statistics of this distribution of galaxies without implementing some form of evolution through gravitational instability, as well as some flavor of dark matter. And so, in fact, our statistical understanding of this distribution of galaxies is key to informing models of cosmology. And this is a digression, but one of the most common statistics that we use are point correlation functions. And so you might collect, you might look at the distribution of pairwise distances between galaxies in the universe, and we see a characteristic peak in that corresponds to certain theoretical expectations of the nature of the universe. This video will now zoom out all the way and then zoom back in, so I'll spare that for the sake of time. But what I wanted to show you here is some understanding of how this structure forms. And so as I said earlier, it is as a result of gravitational instabilities evolving over time. And so the argument that we make, and has been quite well verified through observations, is that in the initial phases of the universe, just a few 100,000 years after the Big Bang, you have this distribution of matter that is essentially almost random, but there's sort of Gaussian perturbations in the density field. And over time, these evolve and accumulate more and more matter because gravity is related to this density. And so you begin to form these web-like structures in which galaxies tend to live. And so this is what forms the cosmic web, where you have vast empty regions that tend to not have galaxies in them, which are called voids, that are sort of broken apart by these large cosmic filaments, which when they interconnect form large clusters that contain hundreds, if not thousands, of galaxies. Now you might say, well, this is fascinating. Why should I care? Or why did you care, Mehmet? And the answer to that is that the environment that a galaxy lives in has a profound impact on its evolution. This is the last video, but this is, we've been zooming in now. And this will now show you the evolution of visible matter within galaxies inside one of these clusters, going all the way from the beginning of the universe to, a few billion years later. And as you'll see, the brightness increases. That actually denotes the density and temperature of, it's just the density. And so you saw that we went from a rather homogeneous field to a very sort of dense field of filaments where galaxies that are at these intersections are encountering each other. And I don't know if the resolution of the video is too low. You can also find this video on YouTube. But what you'll notice when you watch this carefully is that galaxies that are in more dense environments tend to interact with each other greatly. And by interaction, we mean dynamical interactions where they come close enough to each other that the mutual gravitational attraction actually pushes gas out from the galaxy. And you might see this here in some of these trails of gassy vapor that are sort of being blown back through galaxies. That's a process that we call ram pressure stripping, where if a galaxy is falling into one of these dense environments, the hot gas is actually pushing the other gas, the cold gas, away from it. All of this is to say that galaxies in different environments exhibit drastically different properties. And we're able to observe this. When we look at galaxies in very dense parts of the universe, we see that they are often quite large, red, and bereft of gas, which means that they are no longer forming new stars. Conversely, when we look at galaxies that are in less dense regions, we often see that they have a reservoir of cold gas, which they can then use to form stars. And so this dichotomy is one that we observe quite easily, but the missing link here is how this connection is related to dark matter. And again, I'll discuss that briefly in a minute, but how do we get this data in the first place? So I wanted to give a perspective of some history. This is, in our community, is known as the CFA stickman. The CFA is Harvard Smithsonian Center for Astrophysics. And this is a figure that shows the positions of galaxies, where each point again is a galaxy. This sort of arc circle along the top is showing you the right ascension, which is an absurdly archaic unit that we use to denote position along the sky from left to right. Think of it as theta in spherical coordinates. And then the sort of straight line here denotes the radius. And it's shown in recession velocity, which is the speed at which galaxies are moving further away from us, but we have ways of relating that to distance. And so this image, gained a lot of attention because it shows this sort of stick figure. And one thing that's quite interesting is that it took them months to gather the data to make this observation. But now these days, this is just a tiny tile out of this very vast network that we're able to observe. And so those 400 galaxies in that previous image that took months to observe, we can observe thousands of galaxies per night now using modern technology and specific, instruments on telescopes. But again, the reason I'm showing you this figure is to reiterate this distribution of galaxies being quite unique. So again, this is a top-down view of a slice of the universe where the color coding represents the density along the line of sight. And we're seeing, again, these very dense clusters of galaxies that are interconnected with linear structures called filaments, and they surround voids where we see very few galaxies. So yes, as I said before, we know galaxies are profoundly influenced by their local environment. But the thing is that local environment itself is profoundly influenced by the underlying dark matter. The reason we say this is because galaxies essentially serve as lighthouses for dark matter. Galaxies only form in regions of space where dark matter has already accumulated and created a gravitational potential well. Now, the dark matter budget of the universe is unknown to us, but more importantly, the exact distribution of dark matter is currently unknown. There are different flavors of dark matter that we can utilize, particularly ones that relate to different temperatures of the particle. And each one of these models produces a different prediction of the distribution of dark matter, and in particular, the quantity of dark matter that exists. So a better understanding of the budget of dark matter is essentially crucial to unlocking some of the mysteries of what exactly this particle is. But it also serves as another benchmark for us when we look at how galaxies evolve as a function of their environment. So essentially being able to quantify galaxy properties changing as a function of this dark matter mass is a very open problem. And so this is a question that interests both, the big picture cosmologists, as well as the folks who are interested in galaxy evolution like myself. Now, environment is typically measured by essentially pointing a telescope at a chunk of space and finding as many galaxies as possible. But in the text here, I said that this is expensive. And what I mean by expensive is that it takes a significant amount of time to precisely measure the position of a galaxy using a galaxy spectrum. That's because it needs to accumulate more, the instrument has to accumulate a significantly larger number of photons to be able to deliver a good signal. However, what we can do is instead look at photographs of space. And so there, the problem becomes a little more tractable because you essentially take your telescope and you point it at a chunk of sky and just let the CCD detector collect photons for a while. And so that's what I refer to by these photo-Z measurements. These are actually what we call photometry, is the measure of just the photons coming from galaxies, and spectroscopy is when we measure the spectra. But photometric measurements are always improving, and they're giving us handles for distances to galaxies. However, we still haven't quite built a telescope that can observe dark matter yet. So is there some way that we can connect the observational properties of galaxies to the underlying dark matter that surrounds them? And so the reason why environment is particularly important, I wanted to highlight in this figure, is, so these are two simulations of galaxy clusters, and these clusters have been called Amun and Supai. And the primary difference between these two clusters is that they have the same amount of dark matter within the circles that we've shown here, but they exhibit different environments. So the one on the left is in a much less dense environment, and the one on the right is in a much denser filamentary environment. And the color coding here represents the velocity distribution of dark matter particles that are flowing into these halos. This is a complicated figure, but the main take-home message from this is that even environment influences the inflow of dark matter particles into galaxies. And so the very dark matter halos that will form will vary as a function of environment. Therefore, the galaxies that form in those environments will also be varied. And in fact, the number of galaxies might differ, or the dynamics of the way they fall into these clusters may differ. So this is an open problem. Now, what we defined in a recent paper is a concept called total satellite luminosity, which I'm going to call Lsat for the remainder of the talk. And this will be something that I refer back to quite often. Now, this is essentially a new technique for studying the connection between the galaxy and its halo. Just to sort of not get lost in the jargon, when we refer to a halo, we're referring to the distribution of dark matter around a galaxy or a group of galaxies. So I tend to use these words interchangeably, but often if I'm talking about a dark matter halo, you can assume that I'm talking about the distribution of dark matter particles that surround the entire group of galaxies. Now, what was shown in a paper written by my previous advisor is that the total brightness of galaxies that surround a central galaxy can actually be correlated quite strongly with the dark matter halo mass. And so just to define some words, when we look at a cluster of galaxies, we see a central galaxy, which we consider to be at the center of the gravitational potential well. And then all of the galaxies surrounding it that we think pertain to that group are called its satellites. And so there's a very tight, very statistically robust relationship between the total brightness of these galaxies, excluding the central, and the mass of the dark matter halo that envelops them all. And so this connection was developed using simulations and then was backed up using observational data. But the work that I'm really going to talk about is how we can relate the observable properties of the central galaxies to this Lsat variable. And I'll discuss why. But firstly, I just want to show a very, very straightforward schematic of how we do this. We really so we have these galaxies, all these points are galaxies. The blue stars are centrals and the yellow points are satellite galaxies. And so what we do is we take our centrals and we drop circles on them. KPC here stands for kiloparsec, or thousands of parsecs, and 1 parsec is 206,965 times the distance between the Earth and the Sun. So it's 209,000 AU. And it's been a long time since I remember what that was in meters, but it's a big distance. And so we place these circles around these central galaxies, and any satellite galaxy that falls within this region, we simply tally up its luminosity. It's a very straightforward process. Now, there may be some galaxies that are in the foreground or the background of the group, but are not part of it. So say, for example, there was a galaxy that's much closer to us, but is in the same line of sight. That would be an interlopal signal. So what we also do is measure the average amount of satellite luminosity in regions of space where we don't detect any centrals. So think of this as like a background subtraction. But ultimately, the signal that we get is really an analog for the brightness of the objects, the yellow objects that are in these circles. So this is just showing that same information again as a refresher. But again, the idea is that the brightness of these satellite galaxies is correlated very strongly to the halo mass that surrounds the entire collection of galaxies. And so this is just a figure that relates this. Unfortunately, in extragalactic astronomy, we use indecipherable axis units. They're laden with jargon, but essentially along the x-axis here on the left panel, we're showing you the mass of the dark matter halo in units of the mass of the sun in logarithm space. And on the y-axis is the satellite luminosity within a certain radius. And the correlation here is quite tight. The error bars that are quite minimal here come from bootstrapping the sample. And the fit is, I think, has an error of, I forget exactly how much it is, but the correlation is about, the alpha is about 1.1. So it's quite tight. And we also see a similar relationship between the satellite luminosity and mgal on the right-hand plot, which is the stellar mass of the central galaxy, again, provided in units of the solar masses. So one solar mass is about 2 × 10⁻30 kilograms. So these are heavy things. So let's accept that the connection between total satellite luminosity and dark matter halo mass is true. Then how can we further simplify the connection between galaxy properties and dark matter halo mass? This is really the problem that we were trying to tackle. But more specifically, is there an easily observable property of a central galaxy that correlates strongly with Lsat, and therefore correlates strongly with dark matter halo mass? If this exists, then it turns the problem of measuring the total dark matter mass budget of the universe into a much more trivial problem. So I want to briefly discuss the sample that we gathered. I won't spend too long on this, but these are just showing you maps of chunks of the sky where we gathered our information. The key thing here, ignoring all of this, is that we have a sample of galaxies that is spectroscopically identified, but also overlaps with a field of galaxies that we observed with imaging. And so we are able to determine our central galaxies using the spectroscopic information, but then use the background imaging to get these luminosity measurements. The satellite, whether or not a galaxy is a central or a satellite is defined just through this very straightforward probability. It just goes from 0 to 1, obviously, and it's as a function of the probability that a galaxy is a satellite given its projected distance from the central galaxy. So this is projected onto a 2D field, as well as it's the probability given its distance along the line of sight. So it's a two-dimensional measurement, and we essentially very conservatively use a cutoff of 0.9, PSAT of 0.9 to define a central, to define satellites. Anything less than that, we assume is essential. So we have a very, very clean sample of, sorry, I'm getting mixed up. So from PSAT, we can calculate P central, which is just 1 minus PSAT. And we use a P central value that's very high of 0.9 to be able to cleanly define our central galaxies. But that's besides the point. We then collect a set of galaxy properties. And this really is just catalog bookkeeping. These are various observable properties of galaxies. Concentration measures really just how concentrated the light of the galaxy is. The effective radius is a measurement of size. Velocity dispersion measures how rapidly this galaxy is rotating. Specific star formation rate tells us how many stars are being formed in the galaxy. The stellar mass density is simply the size of the galaxy divided by its stellar mass. R-band magnitude is a very convoluted word to say how bright the galaxy is in a given camera filter. 4,000 angstrom Bragg is a spectral signature that tells us about the young stellar population of the galaxies. And the Sirsic index is just a number that encodes sort of the morphological distribution of light in the galaxy. I know that's a lot of jargon, but these 8 properties essentially provide a nice summary of both the stellar population of these galaxies and their shape and appearance. But most importantly, these are easy to measure, especially things like the luminosity, the R-band magnitude, the effective radius, the concentration. These are what we call cheap data for us. We can point a telescope at the sky and get this information easily. So what I want to show you is the correlation that we see, the results that we see. So on the left, on all of these plots that I'm going to show you are showing you the same thing. But to remember here, we have for every galaxy, these cataloged properties followed by the satellite luminosity as well. And so on the left-hand side, I'm plotting satellite luminosity as a function of the stellar mass of each central galaxy. And then I split in every bin of stellar mass, I split the distribution in bins of quantiles of velocity dispersion. So just to sort of recast that, the idea here is that if we see a strong separation in these trend lines, which we do see, and so these error bars, just for the sake of accuracy, are just 1,000 bootstrap resamples. The separation here of data points suggests that the satellite luminosity is a strong discriminant of the velocity dispersion. Rather, if this were not the case, then we would see something drastically different, and I'll show what that is. The right-hand side of the panel is perhaps a little easier to interpret. It's the same data, but now I'm plotting satellite luminosity as a function of this velocity dispersion, and now binning by stellar mass. The binning by stellar mass here is important because we typically assume that stellar mass is the most important property of a galaxy for defining all of its other properties. But what we're seeing here is that independent bins of stellar mass show us strong trend lines for Lsat as a function of these various galaxy properties. Here's what would happen if we randomize the data. So here now, the velocity dispersion value of galaxies has just been reassigned at random. And you see here how the signal disappears. And this is what you would expect to see if Lsat was providing us with no information. On the left-hand side, the points are all clustered. On the right-hand side, we see totally flat distributions of points. So Lsat shows no trend with velocity dispersion in fixed stellar mass bins. So just to sort of flick back and forth between these two again. And so we present these results for a number of galaxy properties, and I won't go through these in great detail. The paper has several of these, but we see strong signals. Now, the one interesting thing that we began to do after this is said, well, okay, let's look at different combinations of galaxy properties as a function of Lsat. So these are now simply two-dimensional histograms, with smooth contours overlaid on top of them. And you can see that we can use these plots to get an idea for which property impacts Lsat more. So to give you an example, say looking at the top left plot, if the contours were effectively vertical, or rather the gradient in the two-dimensional histogram was purely horizontal or purely vertical, then that's a strong argument for only one of those galaxy properties influencing the total satellite luminosity. But this sloped gradient in the two-dimensional histogram suggests that there is perhaps some hierarchy of which properties interact or are most correlated with total satellite luminosity. And this is what, quantifying this, getting some understanding for, which galaxy property should we be looking at to get the best correlation with Lsat is what eventually led us to using mutual information. And so when we first looked at these plots, we, scratched our heads a little bit and weren't quite sure how to address, quantifying this difference in correlations. And so I spoke to a friend of mine who worked at the Center for Data Science at NYU with a background in statistics, and he said, oh, try mutual information. And so we did, and it was, I think, quite successful. So just to reiterate, again, visually, it is easy to see the striking way in which all of these properties correlate with satellite luminosity, but we want to quantify this more formally using information theory. So for those of you who are not familiar with it, mutual information is essentially, the formal definition is that it calculates the mutual dependence between, or quantifies rather, the mutual dependence between two random variables, X and Y. So more specifically, actually, it provides you with the amount of information in bits that can be gained on Y, given knowledge or observations in X. And so this has its background in information theory. If any of you are familiar with the Kullback-Leibler divergence, that DKL parameter is exactly that. And so you obtain it by looking at the probability distributions of these two variables, X and Y. Now, the nice thing about mutual information is that it is essentially, we're not assuming any model for the distribution of data. And it's equally useful for us, even if it's, it'll work for categorical data sets, it'll work for continuous random variables. And so in this case, actually, we assume that that we're dealing with continuous random variables. So in fact, if you take the Kullback-Leibler divergence, or the mutual entropy if you want, then say you have two continuous distributions of continuous random variables that are P and Q, then you can define DKL using the equation below. And so then if you take that, put it back into the equation for mutual information, you end up with this expression here, which is much easier to understand if you realize that the top is the joint probability distribution of X and Y, and the denominator is the marginal probability distribution between X and Y. And so this relationship then encodes this bitwise correlation between the two parameters, X and Y. Now, mutual information is symmetric. The mutual information on X given Y is the same as the mutual information on Y given X. If X and Y are completely independent of each other, then the mutual information is obviously 0. And if they are totally correlated, or rather if they are collinear, then the mutual information of X gives you the uncertainty in Y, and vice versa. So the plots that I'm showing here in the middle are figures that we created more for our astronomical community, because we tend to think of things in signal to noise ratios, which is really just how much of your information is signal divided by how much of your information is noise. And so I generated just a straight data set that had, linear correlation, and perturbed it by a certain amount of Gaussian noise in order to achieve a degrading amount of signal to noise, and then computed the mutual information between these. And so the thing to see here is, as signal to noise decreases, mutual information decreases as well, as you might expect. But we felt that these plots gave us some understanding of, what these numbers should look like, because when you're dealing with bits, especially for us, it's a little abstract. It's hard to sort of understand what exactly the numbers really represent. And so we were able to compute this for synthetic data. And just for the sake of bookkeeping, we used an algorithm written by Party and collaborators. And this was provided by an R package called MPMI. Works straight out of the box, calculates mutual information nice and smoothly, really makes life easier. And again, very happy to keep using R to do all this. In astronomy, there's not a lot of R users. And so we always like to promote when things go nicely. So we wanted to, the reason we actually showed signal to noise ratio is that we were actually able to calculate the signal to noise ratio on the total satellite luminosity as a function of stellar mass of the galaxy in simulations. And so taking that same distribution of signal to noise values and then calculating mutual information between this linear data set by applying noise such that the signal to noise ratio values are equal to the point shown in the left plot, we were able to sort of show a distribution of values for mutual information going over to just a little over 1. So again, this is just for context, just to give you an idea of the numbers involved. And so we summarized what we found essentially by calculating the relationship between any given of these observables that we define as X and satellite luminosity. And so it's just pairwise mutual information calculations. So these bar charts show that number and show the galaxy property associated with them. And the color coding here is similar between all of the different plots, but I haven't really discussed what quiescent and star-forming galaxies are. It's not that important. They're just relating to sort of the star-forming activity in galaxies. And the main thing to take away from here is that we expect these two populations of galaxies to be different. And in fact, it's reassuring to us that we see different hierarchies of galaxy properties for these samples. But the striking thing to us when we looked at this data or these results is you see here this MR, this is the R band luminosity, or how bright the galaxy is, shows a stronger mutual information result than the stellar mass of the galaxy. And this was surprising because, again, the accepted standard in the literature in extragalactic astrophysics is that the stellar mass of a galaxy is the strongest predictor of the dark matter halo mass. In fact, most models for predicting the dark matter halo mass of a galaxy only take into consideration its stellar mass. They have no other variables involved in them. And this is in fact an open problem in the field as we're beginning to discover that this is not true. And there's a whole body of literature related to this called galaxy assembly bias, where we're beginning to see that there are other properties that influence the formation of dark matter halos and this distribution as well. But this presented us with a nice sort of hierarchy of which of these properties of the central galaxies we should look for to then get a good estimate of the halo mass of the galaxy. And this was great to see because MR, again, this brightness of the galaxy is incredibly cheap to measure. You can just point your telescope at the sky and scan along, and you will receive some photons from each galaxy and be able to measure this luminosity, compared to stellar mass, which is notoriously difficult to measure. Stellar mass is measured by taking a spectrum of the galaxy and then comparing that spectrum to various templates of different galaxies with different stellar populations, and then synthetically altering how far that galaxy is. And it involves dozens of assumptions on how much dust there might be in the galaxy, so on and so forth. It's a messy business. Brightness, luminosity, that's easy to get. So this was good news. And so again, I'm pointing out here that stellar mass really falls down in the ranks in terms of mutual information between that property and satellite luminosity when we look at different populations of galaxies. Here are just some numbers. I won't spend too long on this. But one thing that we were interested in looking at was looking at the sort of change in mutual information in bins of fixed stellar mass. So I've talked about bins of fixed stellar mass quite often here. And the reason I bring this up a lot is, again, we expect stellar mass to have a strong correlation on galaxy observables. And so it's a nuisance parameter in this analysis, right? If you see a distribution, if you consider a sample of galaxies and consider their full distribution of full stellar mass distribution, then any correlation that you detect between those galaxies and some secondary property is more often than not being driven by the trend between that property and the stellar mass of that population. And so when we try to study the impact of these properties on galaxy evolution without that nuisance parameter, we do this binning by stellar mass. And that's precisely what we've done throughout the paper and inside these figures here. So what these figures show is the change in mutual information between, the change in mutual information when we compute the mutual information between total satellite luminosity and one of our 8 observable parameters, and the mutual information between total satellite luminosity and the stellar mass. Just what that means then is that if this delta MI parameter is greater than 0, then the observable in question is giving us more information on total satellite luminosity than stellar mass. If it is less than 0, then stellar mass is performing better. And now we were able to show this as a function of the stellar mass. And this figure is a little hard to decipher, but one result that I wanted to point your attention towards is the central panel here. So what we're seeing here is that as we go towards higher and higher values of stellar mass, we see an increase in mutual information between all of the observed parameters compared to stellar mass. When we first saw this, we were a little surprised, but then we were able to sort of explain this by reasoning the following. Quiescent galaxies are galaxies that are very old and they're very dead. In fact, we often call them red and dead galaxies. Quiescent galaxies at the very massive end of the galaxy mass scale are almost always found in the same kind of environment. That is to say, they are almost always located at the very central regions of very, very massive dark matter halos. You will very rarely find massive quiescent galaxies in the field, or what we call the field, which is empty regions of space where we don't expect there to be a lot of dark matter. And so what we're seeing here is the direct result of the homogeneity of the environment of these galaxies, because now the stellar mass is telling us, well, once you're at this high stellar mass, you're always in the same environment. It's only the small subtle changes in your other properties that might be giving us some indicator of the dark matter environment that you live in. So for example, if the dark matter halo has a lot of inherent spin, then you might expect the velocity dispersion of the galaxies inside of it to also be high, because that spin, that kinetic energy, is transferred from the dark matter particles directly to the baryonic particles. You know, even though we can't observe dark matter directly, those gravitational interactions continue to persist. And so we see that exchange of energy and that exchange of kinetic energy in particular. And so we thought this was quite fascinating. And you know, the jumping around of all of these different rankings, you may have noticed that the rankings here don't follow the rankings in the previous slide. And we argue that that perhaps is showing that we may have some bias here in our results when we look at everything as a function of, you know, without binning in stellar mass. Yes, and so this we thought to be an exciting result. And so we're able to show again that there are differences in these correlations, and that these differences in mutual information values between star forming and quiescent subpopulations, we argue, is almost, if you squint, you can almost see it in the data, although perhaps this is maybe utilizing it a little bit of creative licensing. But you know, essentially what this translates to is that the slopes on some of these are a little steeper, particularly for the quiescent population of galaxies. But you know, this was not a point that we made very strongly in the paper, because I think it takes some interpretive liberty. But the idea here is that these quiescent, so the take-home message from all of this is that we are both able to measure the properties of these quiescent galaxies better for various reasons, and also that these quiescent galaxy properties have higher values of mutual information for the total satellite luminosity, and therefore we expect them to correlate better with dark matter halo mass. So I'll just summarize in a few minutes, but I do want to show a couple of slides after this to show, you know, about some interesting work that's coming up. But just to reiterate, we have this new parameter now called total satellite luminosity, and it is indeed a powerful metric for exploring the galaxy to halo connection. It basically allows us a way to get halo mass estimates at very high fidelity to a few orders of magnitude below what is currently possible. So I want to expand on that point a little bit. Up until this point, we have had other observational methods for determining dark matter halo mass. And the one that has been most popular is a technique that we call weak lensing. Weak lensing consists of measuring the gravitational distortion of dark matter, Weak lensing tells us, we measure that by looking at how distorted the shapes of galaxies are, because the dark matter that surrounds them effectively bends the light that is coming to us, to our detectors, as they go through that gravitational field. And so the way weak lensing works is that we take thousands of images of galaxies, we stack them up on top of each other, and generate what we call a shear profile. And the shear profile is really just a measurement of the deviation from sphericity of a galaxy. So it's really, we're just measuring how elliptical it is. And then that ellipticity is then correlated with the amount of dark matter in that particular field. This works, but it is fiendishly expensive to measure, because you need unbelievably detailed images of these galaxies. You can't have any atmospheric aberrations in your optics. You can't have any distortions in your image. And so the only telescopes that are capable of doing this around the world are located in deserts, or, you know, in very high altitude areas, or in space. And so this data is difficult to come by. But Lsat actually allows us to estimate dark matter halo masses to a few orders of magnitude below what we can do with weak lensing, with less error. So the uncertainties in our estimates are much lower compared to that technique. So as I mentioned at the beginning, this Lsat value scales almost linearly with log halo mass. And as I showed, there's a number of galaxy properties that perform better than stellar mass when correlating with this total satellite luminosity, when we measure them with mutual information. And I don't think that this measurement, the way in which we were able to quantify this would not have been possible without utilizing this technique, because we really couldn't come up with any other way to robustly estimate this correlation in a way that didn't introduce more uncertainty into our analysis. And in fact, the referee report it left the mutual information stuff well alone. I think they were quite happy with it nicely, but perhaps that's just astrophysics reviewers, who knows? And so to end, really, I just want to say, well, this then led to the next question, and this is the result of a paper that's currently ongoing, which is that, well, then why don't these stellar masses perform best? Because that is really what we expect from our background understanding. We have strong priors for stellar mass performing well. And I want to show that through these somewhat convoluted plots. But the idea here is, if there is a strong correlation between total satellite luminosity and R-band stellar magnitude, then at fixed values of R-band stellar magnitude, there should also be a positive correlation between satellite luminosity and stellar mass. So there's three parameters at hand here. There's the satellite luminosity, the mass of the galaxy, and how bright the galaxy is. If at fixed values of R-band luminosity, we do not see a positive trend between stellar mass and total satellite luminosity, then that suggests that there may be some systematic errors in the measurements of stellar masses, because we expect that trend to be essentially to follow along both axes. It's almost as if, I perhaps shouldn't say this without being sure, but it's almost a sort of a fundamental plane, right? You have this sort of strong positive correlation between these two parameters. And so we're currently undergoing a study where we have a sample of galaxies for which there are a couple dozen stellar mass estimates that are openly published and available. And we're essentially computing these relationships between all of these publicly available stellar masses and showing that these distributions vary greatly. And so perhaps the reason why we didn't see a strong correlation between stellar mass and total satellite luminosity compared to R-band magnitude goes back to what I was saying earlier about how this parameter is much, much more complicated to measure. It could just be that all these different techniques of measuring stellar mass have significant uncertainties associated with them, and the physical model-based assumptions that are made in each one yield stellar mass estimates that are less precise compared to these luminosity measurements, which are often very easy, very precise, and have low uncertainties associated with them. So perhaps if we do come up with a better way of measuring these stellar mass estimates, it would be interesting to revisit this result and see if the mutual information values change at all. So just to go back to the summary slide, another topic that we're exploring at the moment is, again, using this Lsat as a value of environment to study the environments of black holes, which is leading to some interesting results as well. And again, it allows us to do higher fidelity measurements. The one thing that I wish we had done in retrospect is looked at multi-information, which for those of you who aren't familiar is really just the concept of mutual information, but this time applied to linear combinations of various parameters. And so it may have been interesting to go back and see if there are different combinations of observable parameters that tell us more about this satellite luminosity, but that's perhaps a project for the future. But in the interest of time, I will stop there, and I'm happy to take any questions. Thanks.
Awesome work. All right, let's see what questions people have.
Sorry, I think you're muted.
Oh, yeah.
I am muted.
Okay.
In the chart of the mutual information, that the more, that one, you have one that goes completely the other way.
Yes.
What do you know why that is?
Yes. So that population there on the right are purely star-forming galaxies. So these are galaxies that are much more rare at high stellar masses, because typically by the time a galaxy reaches that state of being that massive, it has transitioned from being a star-forming galaxy to being a quiescent galaxy. And so we hypothesized that those results are due to low number statistics. And so we're simply just not seeing enough galaxies in our sample to be able to make these measurements accurately. But that's a good spot. And so subsequently, that should also be said that we typically see very few quiescent galaxies at low stellar masses, which you may have seen, in fact, for that central plot, the range of values in the x-axis is different, precisely because we just don't see enough of these objects at masses lower than 10 to the 10 solar masses, because they're just, you know, the physical processes that govern the transition between star forming to quiescent, or from spiral galaxy to elliptical galaxy, often tend to segregate galaxies into different stellar mass environments.
I have a question, if
Sure.
I may. In completely different field, I used to work with different information measures, and in some cases, measures like hindered distance have certain advantages versus Kalbeck-Leibler. I wonder if you tried or had an idea of using other information measures in your situation.
No, unfortunately, we didn't. We perhaps somewhat blindly found this one and thought, oh, this is good. And this gives us good results. But I think it would be interesting to repeat the measurements using all of the different metrics to see if it's robust, certainly. I didn't go into it, but we did make some attempt at measuring uncertainties in our measurements, but we weren't, you know, we did things like jackknife resampling of our population of galaxies and then recomputing the mutual information. We also have error measurements for each of these observational properties for every galaxy. And so we assume that these errors are distributed normally around that measurement. And so we actually repeated the process where we generated, you know, several thousand samples where we perturbed the observed measurement of that galaxy property by the uncertainty associated with it and generated, you know, sort of a normal distribution of properties for every single one, and then propagated that through the mutual information calculation. And in all cases, the errors that we obtained were lower than the associated errors from jackknife resampling. So we, you know, we were careful, but I do agree that had we been aware of other techniques, we should have used them. Yeah.
Thank you. That's really very interesting.
So how much statistics did you know before you started this project? Like, did you have to learn this to do this, or did you already know this stuff?
I had to learn the mutual information to do it, yeah. So I cracked open several textbooks, which I hadn't done in a while. But often, and you know, perhaps this is a bit of a digression, but astronomy is a little bit slower, I think, when it comes to the uptake of modern statistical methods compared to some other fields. For example, Gaussian random processes, or Kriging, you know, that's been in common use in geophysics since the 70s. But it has only recently become relevant in astrophysics because it turns out that it can be used very nicely to model the transits of planets passing in front of their stars. And so when you see this dip in the brightness of the star, that often can be modeled very well with the Gaussian random process. And so often we tend to rely on more traditional methods of statistics, and when something new like this is incorporated, you know, I've given this talk a few times now, and I have not yet met another astrophysicist that knows what mutual information is without me having to bring it up, which is why we made these figures, because we knew that we had to explain it in more understandable terms to our audience. And so the appendix of the paper is really just, this is what mutual information is. So yes, I had to do a fair bit of background reading. And I think that's been a constant for any time I've tried to use a more interesting statistical method in my work. There's a whole chapter of my thesis where I did adaptive density kernel estimation, which again, I'd never run into in my undergraduate studies or my graduate studies, but I picked up I think it's the Silverman book from '83 and learned it from there. So yeah, it's often what happens.
Are you still doing this stuff? Because in the introduction, she said that now you're a data scientist. Is that?
I am, yes. So my day job now is as a data scientist, but my advisor and I are still sort of talking on Slack, and we have referee reports coming in, and there's still a couple of extra papers from this that we're trying to publish. Although I am using mutual information at work. Yeah, primarily within the context of trying to understand, you know, I think it comes up quite often when you're looking at things like machine learning or supervised learning, when you're doing things like feature selection and feature extraction. I found that using mutual information provides us with a more robust estimate of feature importance, particularly when compared to something like a PCA, because in mutual information, you're not assuming that there's a linear correlation between the principal components, and that can be quite nice. Sorry, go ahead.
No, I've never seen that.
Yeah.
I mean,
and you know, the other one is, you know, I've often found my new colleagues now tend to really like to use things like random forest regressors to use, you know, the importance mapping of the output. But then when I ask them what they think that means, they don't know what the answer is. And so mutual information provides us with a better, with a more concrete answer for why certain properties are better related to certain things. And so I think within this idea of, you know, dimensionality reduction, feature extraction, it still features quite prominently, and I enjoy being able to use it.
Thank you.
Thank you very much.
Any other questions from anyone? Okay. I think we can wrap up then. So
enjoy the rest of your Friday.
Yeah, you too. Thank you so much for coming in and teaching us all this stuff.
Absolutely. Thank you very much again for the invitation. It's been a lot of fun and I really enjoyed it. And yeah, have a good weekend, everybody.
Thank you.
You too. Take care, everyone.
Thanks.
Thank you.
Thank you.